Was just up here, so yeah, we've had a great run of just amazing people and amazing speakers, and I'm happy to continue it today. So please welcome up from the American Museum of Natural History, Statia Cook.
I'm really excited to be here. This is really neat to see all of these people who are that excited about astronomy to come out on a Tuesday night after work for many people. And today I'm talking a little bit outside of my field. I work on planet atmospheres, but today I'm going to talk more generally about the outer solar system, which is typically considered everything Jupiter and beyond. And I'm going to focus on how we use the outer solar system as a tool for understanding how the solar system formed. So, as a planetary scientist, I think you can break down what we're interested in into three big picture questions. First, how did the solar system form? What are the processes that formed the solar system as a whole and everything in it, from the largest objects like the sun to the smallest piece of dust? We want to know how it formed. We also want to know what the solar system and everything within it is like, and why is it that way. And finally, we want to understand our solar system in context. We want to know, is our solar system typical of systems of planets, or is it atypical, and why is that? So I'm going to focus today on this first question, how did the solar system form? But you can imagine that it's deeply intertwined with these other two questions. You can't understand our solar system in context if you don't understand our solar system and how it formed. And we can't really look at how the solar system formed, so we really only understand that through understanding what it's like today. So I'm going to start with a brief overview of how we think the solar system formed and what are some of the big questions that remain for solar system formation. And then I'm going to talk about one, or hopefully two, of the ways that we are probing these questions in solar system formation, one of which is New Horizons, which is the NASA mission which reached Pluto in July of this year. And the second is work from the ground, and this is more what I do, using giant planets and their atmospheres and compositions to understand how they formed. So this is a cartoon, this is the NASA public cartoon of how our solar system formed. So we should believe it because it's NASA. It has a lot of tiny little font, which you can ignore. I've tried to put the big points in bigger font. But we start with a cloud of dust and gas that was stable, and then for some reason it goes unstable and starts to collapse. When it collapses, most of the material reaches the center, but some of it doesn't. And so the stuff that doesn't orbits in a disk. So now we have a bunch of stuff in the center and a disk, and the stuff in the center continues to collapse until it gets so hot and so dense that you ignite nuclear fusion, and now you have the birth of a star, in this case our sun. Now, the sun is going to affect the disk. Radiation from the sun is eventually going to push out small material from that disk, so all of the dust and the gas. And we know we have planets and other things in our solar system, so they better form before the sun pushes out all of the material from which to make planets. So we do that, and we think how you make a planet is you start with little pieces of dust, and they coagulate into bigger things, which coagulate into bigger things, into bigger things, until you form planetesimals and eventually planets. And voila, you have a solar system. You have terrestrial planets and giant planets and an asteroid belt in between, and outside of the giant planets you have the Kuiper belt, which are remnant planetesimals that never quite formed a planet. And everything is lovely.
Except for Pluto.
There are actually quite a few problems with forming a solar system, and these are just a few of the big ones that people are thinking about a lot. One is called the meter size barrier for forming planetesimals. So planetesimals are the kind of bigger things, so say like a kilometer in size or a mile in size. I said you start with dust and you make bigger things and bigger things and bigger things, and eventually you have the biggest things and then planets. Turns out if you make things that are roughly a meter in size, they will tend to spiral in to your star rather than colliding with other meter-sized things and building bigger objects. And the reason for that is a little complicated, but what happens is you have dust and gas. When dust is really small, it just floats along happily with the gas, and it doesn't spiral into your star. When things are really, really big, they don't care about the gas anymore, so they just power their way through. But meter-sized objects feel sort of a headwind from the gas. They can't quite avoid the power of the gas, and so that headwind causes them to slow down, which causes them to spiral into the star. And we don't know how to avoid this problem. There is no satisfying solution to it. A second problem is once you have these kilometer-sized planetesimals, you need to make planets. We don't have any problems for figuring out really how to make terrestrial planets, but giant planets, what you need to do is you need to build the core of a giant planet quickly so that it's really big, and then it can start eating gas from the environment. And all of this needs to happen before the star blows the gas out of the early solar system. So you need to build a core of a planet really quickly, and we don't know how to do it quickly enough. So this is another sort of timescale problem. We just don't know how to do things fast enough. The third problem is explaining the Kuiper belt. So if you go out past Neptune, there's a whole bunch of stuff out there. And we can understand why there's stuff out there. It makes sense maybe that you would have remnants of this formation of planets, and you would have stuff that didn't quite coagulate into one big planet, and that's what we think the Kuiper belt is. But it turns out if you look at the objects within the Kuiper belt, there are some really big things like Pluto. And if you have these really big things, you expect sort of a distribution of sizes down to the smallest that would get you those big things. So you expect enough intermediate things that would have, happened during the formation. And there's just not enough of that smaller stuff to expect to have ever grown a Pluto. And so that's one of the problems with the Kuiper belt. A second problem is that a bunch of stuff in the Kuiper belt is in what's called resonance with Neptune, which means, for example, in the case of Pluto, every time Pluto goes around 3 times, Neptune goes around twice. So it's in resonance with Neptune. And the way you get stuff in resonance with a planet is through some sort of dynamical event in the past. And so we think that something must have happened in the past of the solar system that moved all the stuff in the Kuiper belt, which got it all stuck in these resonances. And so that wasn't part of our simplified picture of how you form a solar system. So that's just 3 of many problems we have in our picture of how you form a solar system. So it's clearly not a solved problem. We do have some sort of cartoon ideas of how you get around some of these problems. And has anyone heard of the Nice model? It's a pretty famous model in the planet formation community, and it's considered the, some people think of it as how things actually happened, but you should keep in mind that this is a fairy tale. This is a model that's been tuned to match the solar system as we see it today. So it didn't predict the solar system. It took what we actually see, and it said, oh, this is one way you could do that. And so this is a simulation. In this simulation, the inner ring is Jupiter, then you have Saturn. This is actually Neptune. If you remember your solar system order, that's not quite right. And here's Uranus. And all these little things are the Kuiper belt objects. And so what's happening is the system is evolving in time. The Kuiper belt objects are pulling on the orbits of the planets in the center, and eventually they're going to make those planets go unstable. And so I think it happens right about now. Here it goes. So we're a little bit happier here because now we have the planets in the right order. Also, the outer 2 planets have moved outwards. And what this has done is it's driven out most of the Kuiper belt objects, which solves that problem of not having the right distribution of sizes of these Kuiper belt objects. And it also explains how you could have gotten a bunch of these objects in these resonances, because you've moved them all so much that they can have an opportunity to get stuck in these resonances. And so this is a nice model, no pun intended, but it's not what we would call a scientific theory, because it's not necessarily making predictions and then having those predictions be supported by evidence. And so what we want to do is take models like this and try to make more observations of our solar system and see if this is really what we think happened, or is this just a nice fairy tale. Yeah?
Were those actual orbits of the Kuiper Belt objects that were cranked into the sun?
No. So what they've done here is they've run a bunch of simulations and they're what they call n-body simulations, because they put n, where n is a big number, of objects into a code, and they're all basically the same mass. They just some mass that they've picked for their objects, and they've just run the simulations forward in time. And they've done this for a bunch of simulations until they found one that ended up looking like our solar system does. So these objects, we don't know what the number exactly of Kuiper Belt objects would have been in early times, but we assume there would have been a lot. We don't know exactly what the orbits of our planets would have been at early times, but we assume they had to have been more compact and that Neptune had to be inside Uranus. And then we run things forward and we get something that looks like our solar system. And then of all their runs, they picked this one to call the model and to spread to the community. And it's been really well received.
And where do the other Kuiper Belt objects go? Do they go beyond Pluto?
They leave the gravitational influence of the sun. They're just gone.
Does that mean Oort cloud? Past Oort cloud?
Past, gone. Just gone.
Do
Completely
they burn up?
No, they're just floating off in space.
They escape.
Yeah.
Interstellar.
Yeah.
That raises a question. Did any come in toward the solar system? Do we have any, does this time with any cratering events?
So I think that parts of this theory have been, so there's what's, in the history of our solar system, there was an event called the Late Heavy Bombardment, which is what's been used to explain all of the craters that you see, for example, on the moon and things like that. I think that some versions of this theory are invoked to explain things like the Late Heavy Bombardment, but it gets a little bit hand-wavy when you get there, and it's not exactly right in some of those details, but maybe. Yeah?
How does this theory explain the composition of the various planets?
So this theory in itself, so we don't necessarily, this is something I'll try to touch on later. We don't have a firm grasp on the composition of all of the planets, especially Uranus and Neptune, but you can see how the orbits of those planets have changed. So if you think that composition of a planet depends on where it formed, which we do, then the fact that these planets evolved would be revealed within the compositions of those planets. So, for example, if Neptune formed further in on the disk, we would expect it to have a different composition than if it formed in the outskirts of the disk. And so, since we don't have those precise values for Neptune, we can't necessarily say yet how that relates to this theory. But that's one of the things that we're trying to look at. We want to take the compositions of the planets and use that to evaluate theories like this. So I'm going to spend most of my time today talking about New Horizons, which is the mission that is going to Pluto. And so before I tell you what New Horizons is going to do, I wanted to spend a few minutes answering some sort of really basic questions. Why bother looking at Pluto in the first place? Why do we need to go there to look at it? And why should we do this now? So what's the motivation behind New Horizons? So Pluto these days is not super special. It is no longer awarded the lofty title of planet. It's been demoted to minor planet. But Pluto is extremely valuable still in that it is part of a population of objects that serves as our most pristine relics of the era of when planets formed. So when you go into the inner parts of the solar system, like the asteroid belt, say, those objects feel the radiation of the sun a lot more than the Kuiper Belt objects will, and so they're not nearly as pristine. So there are lots of objects, probably trillions of objects in the Kuiper Belt, but even though Pluto isn't the planet of the Kuiper Belt anymore, it's still the largest Kuiper Belt object that we know, and it's one of the closest ones that we know, and so it makes a compelling target. And so we want to go to Pluto to understand the Kuiper Belt as a whole, to understand the properties of the Kuiper Belt by studying an example of a Kuiper Belt object. And so this picture just shows a whole bunch of the big guys that we know about. Why do we go to space? So this is not a rhetorical question. Why should we send a spacecraft? Does anyone have any?
Get closer.
Yeah, that's a really good reason. It's a really good reason. It's probably the biggest reason you would go.
Telescope closer.
Anything else that
You
people?
don't know what it looks like or what it's made out of.
Yeah, there's a lot of questions that you can answer from spacecraft that you can't answer from the Earth. Not just because you get closer, but because there are some kinds of experiments that you can't do from the ground. One other thing that you probably are familiar with that is a problem from observing from the Earth is the atmosphere, and you can avoid that nice and neatly with a spacecraft. So that's another reason to do this from space. There are also a number of drawbacks of sending a spacecraft.
Time and money.
Time and money. It all really comes down to time and money, but not just that it takes a long time to get there, but that all of your technology is going to be old when you get there, because things to be space ready need to have been around for a decade before you even put them on the spacecraft, and then it's going to take New Horizons. It's already been 9.5 years since New Horizons launched, so everything's 2 decades old. One of the consequences of this is that the memory on New Horizons is smaller than you'll get in your average new cell phone. So this is going to be a real problem. And time also affects you in other ways. For example, it takes 4.5 hours for a signal to get from the Earth to Pluto, and then 4.5 hours for a signal to get from Pluto back. So you're not going to be making, spur of the moment decisions and corrections and say, oh, that looks cool, let's go look at it again. You're not going to be doing that. Finally, yeah.
The other problem is the baud rate from Pluto.
The what?
The baud rate, the bits that we get, 160 per second.
Yeah, it's going to take over a year for us to get the data from the flyby back to Earth. So we're going to fly by in a couple of hours, and then we're going to spend the next year trying to get the data back.
The data is slower than the old home modems that we used to have.
It's horrible.
160 bits, not kilobits.
So I think this is most of what we talked about. One other thing is that spacecraft have to be small. You need to launch it into space. You can only put so many instruments on it, and they have to be tiny. So you have to really plan out everything you're going to do in advance. And if you change your mind, tough luck.
So how big is New Horizons? I mean, like Cassini's supposed to be like
New
bus
Horizons
size.
is the size of a grand piano.
Yeah, so it's smaller than Cassini?
It's small. It's small. It's also, at the time, it was the fastest thing we've ever launched from Earth.
Right. Had to get
So,
within the amount of time there.
plus, we want it to be small because we're sending it far, and then we're going to make course corrections. And so we want to put fuel on it and be able to move it around and send it where we want it to go. So why do we do this now? There are a number of reasons, but a couple that actually are pretty cool, I think. One is that by sending New Horizons when they did, they could take advantage of the location of Jupiter at the time, get a gravity assist, shave 3 years off of the flight time. That's no small change. Secondly, Pluto is on an eccentric orbit. It gets closer and further from the sun. So people think that's why we have seasons on Earth, but that's not. It's just that we're tilted. But for Pluto, it actually does go farther away from the sun and get a whole lot colder. And there's been some fear that it will get so cold that the atmosphere will just freeze out. And since we want to study the atmosphere, that would stink. So they wanted to send it as fast as they could. There was a firm deadline. It had to get there before 2020. So that's why they sent it when they did.
2020, when it gets to its furthest, it gets the coldest?
No, that was just, I think it's arbitrary. Yeah.
Yeah. Pluto also is inclined to the
It is,
to
yeah.
the rest of the solar system, and it takes a lot more fuel to get up out of that plane. So we're picking up Pluto while it's at the plane of the rest of the solar system on the same trip. So there's another good reason.
That is a good
Did it
reason.
use more than just Jupiter, like planetary?
No.
No.
Just Jupiter?
Yeah.
Isn't it looking at Ceres too?
No,
No.
but that's Dawn.
Oh,
That's the Dawn space.
But it is going to try to see something else. There's actually no funding yet for it to have a continued mission after it sees Pluto, but they're pretty confident that they'll get the funding to go to some as yet undecided Kuiper Belt object follow-up.
Does it have the ability to see other ones? Like
Well, that's-
in its path that it's heading towards?
Well, they've got to make some course correction to see anything else. It doesn't have to be a big one. They have some limits, and so they found a couple of candidates that are within the fuel that they have available that they can do a course correction and go to. Yeah.
So I'm curious about your comment that you just made about if they get funding, they can continue to use this instrument. Could you explain how that works? I mean, I understand that if you're saying that if NASA can secure funding from Congress, we'll say,
Sure.
then they have still the flexibility to send commands to that.
So part of the instrument design was to make it capable of continuing past Pluto. So they put enough fuel on it so they could do so. They put instruments on it that could send signals further out into the outer reaches of the solar system. So they prepared New Horizons to be capable of continuing past 2015. But the mission that was supported is just through this Pluto encounter. And part of this is, I mean, this is what happened with Cassini as well. Cassini is not in its primary mission stage anymore. It gets continued funding to continue doing science, and it was built to be capable of doing so. But every mission has a primary mission that is either a success or a failure if you meet the primary mission goals. And so typically that's the part that is originally funded.
So is the funding primarily to pay the salaries of the scientists? And
I mean,
so-
at this point, yeah, they're not building new instruments, but they need to support the people who need to work
Who
on the
have to
project
monitor
and
and-
some level of instrumentation to receive signals and stuff.
Because what, do you have any idea what the cost of that launch was? I mean, but so.
It's
I
one
know
of
things have
one of the
changed.
expensive kind of NASA missions. That's all I know. It's in the expensive category.
But given the fact they know that we all know a lot's changed in the last 20 years in terms of our ability to fund the budget. But given the expense and the fact that you just can't put these things out there that often, it would almost seem like ridiculous not to.
They're pretty confident that they will get the funding to do this because of the reason I think you're saying is once you send this out there and it's, once it shows that it can do great science, it would not be very cost effective to just be like, nah, we're not going to do that anymore. But all of these things are battling. Even Hubble goes through funding battles all the time. Is it going to get funding to keep doing science for the next N years or whatever?
Has there been any science from this project at all yet? I mean,
It has been
Oh,
hibernating
absolutely.
almost until now.
Yeah, so it's doing nothing until it gets there.
The first science observations that they've been waking up every year. They've actually been waking up a couple times a year, and taking a little data. The first genuine new science has been this year, and so for a number of weeks leading up to the encounter, there's something like they said 15 weeks of better than Hubble data that they'll be able to get. So they will have a solid chunk of time where they can get new data.
I'm confused as to the shape of the Kuiper Belt. Is the Kuiper Belt,
It's a donut
is it rotating on the plane of the planets?
for the most part, yeah.
Okay, so Pluto is not on that plane.
No.
So why is Pluto part of a Kuiper Belt?
So there are different subcategories of Kuiper Belt objects.
Ah,
There are the regular Kuiper Belt objects, and then there are the
the
ones
irregular ones.
Yeah, so there's a bunch of different kinds, and it's based on their orbits, but we think different things happen to them. So with Pluto, it's trapped in that resonance as well, and so that's what we think is it happened due to some gravitational interaction with Neptune, that Neptune scattered it into this resonance, and now it's in this resonance.
Do they know the width of the Kuiper Belt?
So the main part of the Kuiper Belt is from 30 AU, which is Neptune's orbit, to about 55. But there's stuff going out to something like 100 AU we've seen.
So where would Pluto be in that range?
It's on the inner edge, but it has an eccentric orbit, so it kind of goes out a bit.
It goes inside Neptune's orbit,
It
and it
goes-
goes
yeah.
outside Neptune's orbit.
Exactly.
That's its path.
Goes yeah, inside the orbit and
I mean,
pretty far out.
it's a strange orbit for something that's in a.
It's
in a
very
plane,
strange, but
you know.
it's also remarkably regular, right? Because it's in this because it's trapped in this resonance. Every time it orbits, it's the same path. It's always orbiting 3 times. For Neptune's twice. It's never going to like crash into Neptune. It's very stable. When things are in resonance, they're extremely stable, but they can be kind of wonky looking. It's a technical term.
Yeah.
Yeah.
On the subject of funding, is there some effort being done to turn this into a whole world objective, like the International Space Station is a good example of a cooperation? It looks like to me we're wasting a lot of money because European Space Agency does one thing, another does another thing, JAX does another thing, and the
So I'm
Russian-
not an expert on this, but I know a lot of missions do have at least some level of international cooperation. A lot of times countries will contribute an instrument even. And so that does happen. I think the more friendly we are as nations, the more likely we are to cooperate. So if China does something, frankly, we might do the same thing because we don't have friendly relationships with them in terms of sharing science. But if it's Europe, we do, so we tend to collaborate more.
Do scientists have an idea of the total mass of the Kuiper Belt? Does it equal all the other planets?
It does not. So we think that it was some number of Earths, like say 10, and now it's less than an Earth, so maybe 1/10 of an Earth or something like that. Small.
Really?
It's very small.
Wow.
At its most, it was probably enough to make up like another Neptune or something like that.
But don't they call the objects also the trans-Neptunian
Yes.
TNOs?
Yes.
So would that be more of the scientific name for the Kuiper Belt objects, or just another name?
I don't know the precise definition of a trans-Neptunian object, but I think,
It might include the Oort cloud and the Kuiper Belt in that definition.
I don't know. But Kuiper Belt is perfectly scientific. Yeah.
I believe earlier you said that there was an assessment that where planets formed in the disk determined what they were made of, what their composition was.
Mm-hmm.
And it seems that once you get to Jupiter, you're dealing with all the gaseous planets.
Mm-hmm.
Can you explain the theory or talk about what the feeling is that why from that distance further
Sure.
out, they're all gaseous planets?
Isn't
So-
that the third part of your talking?
I will try very hard not to repeat myself when I get further along. But so terrestrial planets form where things are really hot. The only thing that condense out of being a gas are things like iron, rocky things that are almost always a solid. And so that's what forms your planetesimals, which forms your planets. When you get to Jupiter, ices start to condense out. First, you have water condenses out. And when things condense out into solids, they form planetesimals, which lets you grow planets much more easily. And if you can grow planets quickly, then they will grow big enough that they can eat not only the solids from the disk, but they can start to pull in the gas. And that's why you get gas giants. And so that's why we think that Jupiter on out, you started to get gas giants. Now when you get far, far out there, there's just not as much stuff. The disk gets kind of tenuous, and so it starts to become hard again to form planets, which is why you start big with Jupiter and then it kind of tapers out, and it actually gets kind of hard to even form Neptune, which is one of the reasons we think maybe it migrated outward from a more compact configuration than where we see it now. So that's the short answer of that.
Thank you.
Yeah. Okay, New Horizons. Why go to New Horizons? This is what Pluto looks like from the Earth. That's really what it looks like. This is HST. Yeah, that's pretty horrible. If you take a bunch of light curves, so if you watch Pluto rotate a lot of times and you look for variations in its brightness, you can start to try to map it. And so people did this, they took a lot of Hubble time and they made these guess images of what, guess is sort of a cruel word to the people who put all the work into it. These are better than guesses, but it's still pretty low resolution, kind of fuzzy images of what we think Pluto looks like. And this is what all those artists' impressions are based on. From just this, we can see that there's a lot of contrast on the surface, more than we see on any other body in our solar system. So the brightest stuff and the darkest stuff we see on any surface in the solar system, so that's cool. What we're going to get with New Horizons is more like this image. So this is not Pluto, but this is the kind of resolution, or even better, that we're going to get on the surface of Pluto. So we're going to start to see, the topography. So think of images you might have seen from Cassini, of Cassini's moons, those kinds of gorgeous images with a lot of detail. We're going to have that for Pluto and for Pluto's maiden moon, Charon. We're going to study the atmosphere of Pluto. Pluto has an atmosphere. It's about 5 orders of magnitude smaller than the Earth's atmosphere, so it's pretty tenuous, which is why I said maybe it would collapse when Pluto got cold enough. We're going to study it in many ways, but one of the things we're going to look at is we're going to wait for the spacecraft to go behind Pluto. We're going to look back at the sun and wait for the sun to occult, or Pluto to occult the sun. So Pluto comes between us and the sun peeks out, and we see how the light is affected as it passes through that very tenuous atmosphere towards the limb. And they're hoping to try to find things like hazes with this approach. So that'd be really neat.
Cryogenic volcanoes, or?
Yeah, well, I mean, yeah, we could definitely see that. There's compelling reasons to believe that Pluto might have a liquid ocean under its surface, like we see for other moons of the giant planets, and we'll see it.
Like an ethane or water? Do you think
water?
Liquid water, really?
Water.
Well, that implies you think the surface maybe is a lot of ice.
Yeah. So the surface. I mean, it's icy stuff. A lot of these things have a lot of icy stuff, but it's not just water ice. It's methane and other things.
But how could there? I mean.
So the idea is that you have radiogenic heating on the interior, which releases enough heat to keep it liquid. The other thing we're going to do is we think that this very tenuous atmosphere is escaping from Pluto all of the time, and it's being driven off of Pluto by the solar wind. And so there are a couple of instruments that are going to be looking at the rate of escape of the atmosphere from Pluto. So that's another thing we're going to be looking at. And this is really interesting to us because we think this process happened on all planets at some point, and so we want to understand how planets lose atmospheres. Another thing that's really neat is Pluto is not just a minor planet Kuiper Belt object, it's a system. It has a whole system. It has Charon, which is about half its diameter, but it also has 4 tiny little moons. 2 of these were discovered well after New Horizons left on its way to Pluto, so an extra bonus. And so we think that this system formed from some sort of giant impact early on in the days of planet formation when these things were really new. But we don't know a lot about these guys, especially these really tiny moons. We don't even know their mass to better than an order of magnitude. So we can learn a lot about the system and how it formed by getting a close-up look of all of these moons and trying to get a grasp on their compositions and their masses and things like that. Yeah.
How do you know you're not going to hit one of them?
That's actually a real concern. So one of the early science approach phases, one of the things they've been looking at is, are there any missing moons that we're not aware of that could be there? Make sure we don't collide with them. Also, any just kind of debris. If there was some big collision in the past, could there be just debris orbiting around and things like that? And we want to make sure we don't hit that. But there's low probability of that happening.
2 years ago, Alan Stern spoke at NEAT and talked about the New Horizon mission. And one of the things he said was that he's taking pictures before he gets there and sending them back in case they hit something, so that they have at least something to come back from the science and the pictures of Pluto in case something happens on the way through.
Yeah, I read something that said that there's like a 0.3% probability at this point that there's some unseen debris that's gonna give them trouble. They have, so like I said, you need to plan everything in advance. So they have all these like, you know, maneuver plans and stuff, but they also have a couple of like evasive maneuver plans built in case they think that they're about, you know, well, not about to hit something, because again, 4 hours there, 4 hours back takes a long time to change anything. But they've thought about this. This is actually a real concern.
Isn't this thing traveling like 30,000 miles an hour?
30,000
so
miles
4
an
hours.
hour. You're screwed. If you get an image and you're just like,
yeah,
oh crap,
here we go,
it's
gone.
It already happened. That's why they have a really good telescope.
There's probably a good likelihood that there are other objects orbiting Pluto that we haven't yet seen, right? Other orbiting bodies?
Like other moons?
Yeah.
Well, that's, I mean, yeah, that's what they're worried about. There could be.
So, what are the odds that the actual mass of the New Horizons will affect those orbits?
Wow.
That I don't know. I mean, I think, well,
It would affect it
In a flyby?
Sure.
Only if it went very close to something of comparable mass.
Yeah.
I mean, it depends on the it depends on the relative masses. This thing is the mass of a grand piano and the size of a grand piano. So.
We're going back by something the size of our moon, not quite the size of our moon. But.
Well, that's Pluto, so it's
Right.
not going to affect Pluto. It's
Right.
not going to affect Charon. It probably, those other guys are already 1,000,000 times smaller, I think, than Pluto. They're really, really
they're
small.
70 or 80,000 kilometers away during the
They're really
flight.
far. They are far. So there's no worry yet, but I mean, if there's just crud out there, if there's just space debris, yeah, you might have issues. But I don't know that they're expecting it to be like, you know, a TV asteroid field where you're dodging things all the time. So.
Is this supposed to pass within the system?
Yeah, I'll show you a picture of that.
Yeah.
This is New Horizons. If anyone can pass this around, my husband works for a 3D printing company, so I 3D printed the New Horizons for fun. But this is what it looks like, and this is the entire science payload. It's just these instruments. Everything that's coming out right now is from this instrument. Well, not everything that they're getting, but any images you see are from LORI, which is this long-range reconnaissance imager. And it's the highest resolution camera on the thing. There's also a second camera on part of an instrument called Ralph, and that will be used to take nice color images of the surface. It also has an infrared spectrometer, and in the infrared you can detect a bunch of molecules on the surface, and so we can start to do mapping of the composition of the surface, which will be really neat. ALICE is the UV imaging spectrometer, and that's what you're going to use to figure out what the atmosphere is like. So they look at air glow directly, but also the occultation I talked about. REX is part of the, so this is the big like communication disc, but REX is the radio experiment, which is built into that. And it's going to do another occultation experiment, which I think is really cool because it's going to do the same thing as ALICE, except not looking at the sun, but looking at a radio signal that we're going to send from the Earth and seeing how that passes through the atmosphere. So that's pretty neat. And then these guys are, they're going to look at the high energy stuff. So they're going to look at atmospheric escape and the interaction with the solar wind. And then this bottom thing, this space dust collector thing, that's cool because it was built by students, college students.
When do we expect to see the first images?
They exist.
They're already on.
So this is where we are now. We're almost there. We're practically there. We're going, as was said, 30,000 miles an hour towards Pluto, and we'll be there by July 14th. We've started this it depends who you ask, but somewhere maybe April, maybe May, maybe February, we've started this better than Hubble imaging period, where we're getting images that are better than we could get from the surface. And they've finally seen all 4 of those moons, those little moons, in addition to the 2 big guys of the system. But of all of this, you know, all of this lead up time, the true encounter is going to be really fast, as you can imagine, for something hurtling through space at 30,000 miles an hour.
2 kilometers per second.
It's ridiculous. But this is what it's going to do. It's going to, in this image, you can't really see, but there's these tiny little tick marks. You can see this online if you can't see here. And this is every 10 minutes. So you can see it flying through the Pluto system. So here's its path, here's Pluto, here's Charon. The other guys are a bit further away, so it's going to be within 8,000 miles, I think, of Pluto, and 2 or 3 times as far to Charon.
Don't hit the bullseye.
No, we're
I don't think they're worried about
we're
that.
threading the
But
needle.
not bad.
Yeah, we're threading the needle as opposed to hitting the bullseye.
Yeah, guess so.
So that's kind of saying that the orbit of all the moons is not in the plane of the
It's not at all. It's tilted almost completely
Almost 90
perpendicular to
degrees,
the yeah. So
But
that's
the
neat.
The orbit of the moons is tilted perpendicular?
Yeah.
And so they've picked this path really carefully to do a whole bunch of science things. One of which is to get all those occultations I was talking about. So here at this bottom edge, this is like the sun occultation, this is the earth occultation, and then they're going to do an occultation of Charon to look for an atmosphere. So they've never seen one on Charon, but they're going to look for one. Because it'd be cool if it's there, and you know, what we usually find when we go places is that things are not how we expect them to be.
Usually.
But there are also some other cool science that they've designed into this. Like they're going to try to look at the backside of Pluto using light that's reflected from Charon. We'll see if that actually works, but that would be neat too. So most of the imaging though is going to happen before we encounter it, because once you go past it, there's no more sunlight and you can't really see the surface.
Do you know how quickly Charon orbits Pluto?
Yes.
6.4 days. Yeah.
Right.
Yeah, that's right, because they face each other the whole time, and it's 6.4 days. So there's also a couple days, the last couple of Pluto Charon days, they're going to take a lot of images, even on the approach, to try to look at both hemispheres, and then to try to see some sort of change over a couple of days to see if the ice has changed or anything on the surface. Yeah.
Have they designed any kind of compensation for the motion during the exposure itself?
Of course.
I'm sure.
Yeah, they do.
You know, something like what they had to do in space when they're taking pictures on the ground.
No, there's no atmosphere to distort the image.
Hmm?
There's no atmosphere to distort the image.
Not a question of atmosphere, it's a
Even
question of the
the relative
motion
motion
while
during
the
the-
shutter's open.
Oh, correct. Yeah, they slew the spacecraft.
Yeah, that.
Well, yeah, but that's a relatively slow, insensitive way. I mean, you got the camera open, but the spacecraft is moved during the exposure is what I'm getting.
Well, they tried all these, they did all these instruments as they went by Jupiter. The whole team.
They've gone through the entire. So this is all automated, right? They fed this in, and they said now they just hit go. I don't even think they actually have to hit go.
They tried it on Jupiter.
But they've
just
tried the
for
whole imaging sequence and everything worked flawlessly, which means it's all going to break when they get to Pluto. But it's all flawless at this point. So I think they've worked out all of the possible kinks. They've even done. This is something I thought was really neat. There's a little bit of uncertainty to where exactly Pluto is. So they actually have to take images of Pluto and then go a little bit off the sides to make sure that if Pluto's not quite where we think it is, that they still get it. So I thought that was pretty neat.
How long is the actual exposure per resident approaches?
I don't know.
The pictures that you sent exist already. They were like taken a year ago.
No, recently, yeah.
But it takes a long time to receive it. You got slow rate.
So
when were they actually taken?
They get all these. So all of the data is really slow, but they have capabilities of getting like quick look images basically that are very lossy. So there's some data, but it's not the kind of quality to do the in-depth science that they want to do. So that's how they managed to do this. But the data rate stuff is really important, and the memory stuff I was talking about, because that's why we're not just taking a bunch of data all the time as we get there, because we just can't afford to do that. We'd fill up our cell phone and then we'd have nothing to store our data on it. So I wanted to tie this back to solar system formation, because if you hear people, the party line, why go to Pluto is, this is going to tell us everything about solar system formation. And I actually sat down for a while thinking about, what are the specific ways that New Horizons is going to tell us about how our solar system formed. And here are 3 specifics that I came up with. One is that, as I said, Pluto is sort of pristine, primitive solar system forming stuff. And so if we can figure out Pluto's composition, we'll have a better idea of what the stuff was that formed our solar system. How do you get the composition of Pluto? That's a challenge. We're going to do it from the surface composition, but then we're also going to have to try to figure out what its internal composition is from things we see on the surface. The Pluto system as a whole is an interesting way of exploring the processes that were going on during solar system formation, because it reflects a probable impact during those early crazy days, and tells us something about the processes that were dynamically evolving the bodies in the early solar system. And so, since we don't know the compositions and masses and orbits of those moons that well, this is really going to help us refine our picture of what happened to Pluto in its early days. And finally, one of the features that you can study when you look at surfaces is craters. And this is not a sexy thing to study, crater rates. But what people do is they actually count all the craters on the surfaces and they measure the size distribution of craters. And this tells you about the population of impacting bodies. And why would we study the Kuiper Belt in this way? Because most of the stuff in the Kuiper Belt is so small and so faint that we can't see it. We can't see it basically any other way. So this is our one best way of probing the size distribution of objects in the Kuiper Belt. And the size distribution of objects in the Kuiper Belt is one of the biggest ways that we either support or reject models of the dynamical evolution of the Kuiper Belt objects. So it doesn't sound cool. It's not going to be fun for someone who's going to be sitting there counting little craters, but this is it's going to be extremely powerful, I think. So I want to talk about, switch gears a little bit, but I don't want to keep you guys past your bedtime, so I don't know.
Don't worry about that.
Okay. Feel free to shut me up if I'm, I feel like, you said 20 minutes or something.
No, this is great stuff.
Okay. So spacecraft are awesome, but we only send a few of them in everyone's, each individual's lifetime. You're probably going to get a few big spacecraft missions. And a lot of planetary science we do from the ground. But this is not terrible because there's a lot that you can do from the ground that you can't do from space, actually. And so what I work on is studying giant planets, and one of the motivations that we have is trying to use the compositions of the giant planets to tell us about where they formed and their evolution after they formed. And so this is a big radio interferometer. It's an array of telescopes in California. It's called CARMA. I spent months there as a graduate student. And you can imagine that you can't put this in space because it's too big. So if you wanted an instrument like this, you're not going to send it from space. So again, with my whys and my hows, so in this case I'm asking, why do we want to study compositions of planets, and how do we study their compositions? We kind of talked about this earlier, so I don't know how much I need to go in again, but there are theories for how planets formed, and each of them has different implications for what their compositions will be. There are actually completely different theories for how planets formed from the one I gave you, even the toy picture. Even though most people believe that toy picture, there's still a completely viable theory for planet formation. It has some pros and cons, maybe more cons than pros, where you actually just condense the whole planet together the same way you condensed a star. And so if you imagine you did that, all the planets would look like mini suns. They would have the same composition of the sun. So that's sort of a broad picture, first level, way that you can tell how a planet formed from its composition. But how do you probe the internal composition of a planet? That's really, really hard to do because we can't see the interior of planets. You can't even do that if you send a spacecraft. Even if you send a probe, you can't tell the interior composition of a planet, because if this is a cutout of a planet, in this case Uranus or Neptune, they're practically the same thing. This is the amount you can directly observe. It's this tiny little shell around the outside of the planet. And it's not because, like on the Earth, you have some surface. It's just because you get so thick in the atmosphere that we have no way of probing it. Fortunately, the fact that Uranus and Neptune don't look like the Earth and that they don't have a surface means that there's a very integral relationship between the atmosphere and the planet as a whole. And so the composition of the atmosphere is not the same as the composition of the planet, but it's very, very intimately tied to the composition of the planet. There's no boundary that's preventing material from the interior from affecting the atmosphere. And so we can use observations of the atmosphere and our knowledge of chemistry to use what we see in the atmosphere to infer things about the planet as a whole. Except maybe this core part, so that's kind of worrisome, but luckily we only think that's like 10% of these planets, so. So there are a bunch of elements in our universe. Hydrogen and helium is most of the stuff, and that's what forms most of the sun, and it's what forms most of Jupiter. But the things that we are interested in for planet formation are like the next most abundant things. So carbon, oxygen, sulfur, phosphine, those are the big ones, because those are the things that form the ices that condense at different temperatures and therefore tell us where in the solar environment these planets formed. And so one of the things we're trying to study is oxygen. Oxygen is a big player in communities doing planet compositions, and this is both in the solar system and for people who are studying extrasolar planets. Everyone's interested in the carbon and the oxygen. Unfortunately, oxygen is usually in water, and like on Earth, water condenses into clouds. In fact, on giant planets, all of the water condenses well below the level that you can observe directly. So we can't see water on giant planets. This means we can't constrain the oxygen unless we're really clever. And of course we are. Someone was, it wasn't me. But there's, well, most of the oxygen is in water. Some of it's in carbon monoxide. And through thermochemical models, we can say for every thing of carbon monoxide, how many waters will we expect? So we can convert a number for carbon monoxide, if we could observe it, to a total oxygen abundance for a planet. So this is great. So now we have to measure carbon monoxide, which doesn't condense into clouds. So if we can see that in the atmosphere, we're all set. We have a probe of the internal oxygen abundance of a planet. Unfortunately, there are other ways to make carbon monoxide. So this is a problem. So the big one, which is in this sort of complicated cartoon, is that basically anything containing water enters the atmosphere, goes through a bunch of reactions, and you get CO. And this is what happens every time you put water in, you get CO out. And so now we not only have to measure CO, but we have to somehow disentangle CO that comes from the interior from CO that comes from this reaction from the environment.
Good luck.
But we can do this. The way we do this is through observations of CO rotation lines, which have these awesome funky structures. So you have this like deep line with this like peak in the center. And if you, this is sort of a complicated figure to show in a short talk like this. But if you, this is the contribution to the line, to the brightness temperature, which is this axis here, so the flux that you're seeing, for different offsets from line center. So when you're at line center, which is this black line, all of what you're seeing is coming from the top parts of the atmosphere. And as you go step out away from line center, more and more of what you're seeing is coming from deeper levels of the atmosphere. So if you believe this, we can get a three-dimensional or a vertical picture of where the CO is. And what will happen is if the CO is coming from the environment, you get more at the top of the atmosphere. And if it's coming from deeper levels, it ends up actually being well mixed throughout the atmosphere. So cool, now we have a way of probing where the CO comes from and getting its abundance. And we've done this, and we put limits on the oxygen for Neptune. Neptune's my favorite planet, so I used it for this example. However, these limits are sort of, right now, consistent with a range of theories, and so we need to do this a lot better. The way we're going to do this a lot better was with my absolute favorite telescope of all time, which is ALMA. It's a $1 billion+ observatory that is in Chile. It's very, very international, so for people who like international instruments, this is one. ALMA blows out of the water any other similar instrument that we've had before. So observations that I did as a graduate student in 30 hours of observing time, you can do in a matter of minutes with ALMA, and you can do much better. So we can map all of the planets in our solar system in not just this CO line, but a whole bunch of other transitions that tell us about those other elements that I said we were interested in. So the oxygen, not just the oxygen, but the sulfur and the phosphine, I don't know what else you want, nitrogen, all of them.
Do they do a multi-frequency simultaneously, or is it?
Yeah, so this you get a big, so if you look at this line thing, this is you don't have to do this quite so bad anymore. This is a really broad bandwidth. This is 20 gigahertz of bandwidth. This peak is only something like 20 megahertz wide. So it's much, much narrower. So you need to get really, really narrow, like high spectral resolution and extremely broad coverage. And so this is something that we've only been able to do for the past 10 or 20 years. We just didn't have the technology for it, and it keeps getting better and better. So ALMA will do this even better than anything we've had before. And so this is stitched, all of these little observations were stitched together from different observations, and we won't quite have to do that stitching anymore. So ALMA is really going to give us a glimpse into the interiors of the giant planets and help us to try to figure out where they formed and how. So that's pretty much it. I told you that there are problems in planet formation. I mean, it's all a matter of perspective. On one hand, one extreme, we know exactly how planets formed. On the other, we have no idea. So I lay somewhere in the middle, but it's clearly an interesting object to study, and I hope that you're convinced that it's an important thing to study. New Horizons is going to do a lot for our understanding of not just the Kuiper Belt, but for the solar system as a whole, and so that'll be really exciting. And if you like Carter's visualization stuff, they have this, they're going to do this thing where you can actually fly along the path of New Horizons and see the real data integrated into the software. So you'll actually see the real images that New Horizons takes, on Pluto, put down in the order that they were taken, and it'll be really neat. But there's also, this is just one very small example of the way that we're doing really cool fundamental planetary science from the ground. And the key is really, whenever there's new technology, since we're on the ground, we can take advantage of it and use it. And so that's what we're doing in a bunch of ways. And the last thing I just want to put up, I used a lot of images in this talk that are not mine. I'm not part of New Horizons. I did not do any of those visualizations, and so I just wanted to credit some of the places that I stole those images from. But thank you so much.
Any other Q&A?
Do you have a proposal at ALMA?
I have several. I'm part of several. Yeah.
You had mentioned that Neptune was your favorite planet. Could you tell us why?
Neptune is a really neat planet because it's really, really cold, and yet it's perhaps arguably the most dynamic planet in terms of its atmosphere of any of the planets in our solar system. It has the fastest winds and some of the most violent storms that we've seen anywhere. And so I think that makes it really exciting, especially as someone who likes to study atmospheres and weather and climate and atmospheric dynamics. Yeah.
So when are you going to come back and talk about your line of study?
Well, I was asked to talk about New Horizons, so I was just doing my duty.
Do you think a new solar system could form around with Pluto?
A new solar system?
You know, like a new, like you were showing the image of the Pluto system with its 4 little moons and Charon. So is it possible that things get pushed out from the Kuiper Belt and that starts to form a whole new system that breaks away?
So yes, I mean, so on one level, we think that, not necessarily for Pluto, which is a pretty tiny thing, but for something like Jupiter, its system and its system of moons kind of forms like a mini solar system, in the sense that the satellites form kind of the same way that planets form out of a disk of material around the star. There are a number of differences. The forces that are at work in an early Pluto are not quite the same forces as the solar system as a whole. For example, you don't have that same kind of effect from the radiation pressure from Jupiter that you have from the radiation pressure from the sun. That's going to blow out the gas and dust. So the forces that work are different. Pluto is more all of a dynamical system. So it's just a bunch of rocks that are hitting each other. And so there are no other really important forces at work. And so it's a system, but the way it formed is probably very different from how you form a solar system.
I see.
Yeah.
Is there a wobble to the inclination of the plane in which the moons are of Pluto as it gets closer, further away from the sun?
To the inclination?
Yeah.
That's a good question. I don't know if there's any instabilities with that. Nothing I read said there is.
I didn't mean instabilities, but like.
But a wobble. I mean.
A wobble due to this. But
there's a lot of systems have some precession, so I wouldn't be surprised, but I'm not aware of it. Yeah.
The team of scientists that work on a long mission like this, what do they do when they're not working on it? I know they get funding from the government, but there seems to be a lot of free time. Do they work on multiple experiments? Do they split their time? What do they do with the rest of their time?
So I've never been on a mission. I think for the people who, some people came to speak at the museum about New Horizons, and one of them said that was on the dust instrument design team, and then helped support that instrument, and then went off and did a completely different project for the however many years that New Horizons has just been, hibernating on its way. So yeah, you go off and do something else. I think during the mission, you don't have a life and you don't sleep. And sometimes, the data analysis is enough work to last you after the mission. But yeah, if you have something like New Horizons that's hibernating for all these years, I'm sure there are a bunch of the scientists on the team that have to go find other work to do. And, funding for astronomers is, I don't know how to explain it. Like, you get a grant for some percentage of your time for some amount of years, and you do that work for that amount of time, and then you try to get funding for the rest of your time. And no one is going to fund you to sit around when you're a astronomer unless they have some job, and if they do, I want that one.
One of the things that Alan Stern mentioned in his talk was that the team does simulations. They built another satellite that has all the electronics, is running at the same clock rate, just a couple of days locally on Earth, and the team runs simulations so to make sure the programs work, make sure that the spacecrafts have been told what to do.
Don't have to wait 4 hours.
Right, and they make sure that it's all correct because they only have one shot at it. So there's a bunch of people who, between the hibernations, are figuring out what to tell it to do the next time.
Yeah, I'm not sure that Alan Stern needs to have another job. I think he's got enough on his plate this whole time, probably. Yeah. Yes.
You got me thinking about something I haven't heard about in a while since you were talking about how great Neptune is. What's the story with the Great Dark Spot?
Great Dark Spot's gone, man. It's been gone. So it was there when Voyager went.
Right.
And then we're like, this rocks. I wasn't, because I was like 6. But other people were like, this rocks. And we're going to study this from the Earth once we have the technology. And so then they sent out a Hubble, and they took a look, and it wasn't, and they couldn't find it. So sometime between Voyager and when Hubble was functioning, it went away.
Because I remember they made a big deal of the fact that it was at the same latitude that the Great Red Spot was at.
We thought it, I mean,
it looked like it was,
someone thought it was just going to be there forever. I mean, like the Great Red Spot is. It was just going to last. Although there were some indications, if you really thought about it, that it wasn't, because it was kind of moving. That's never good. You don't want to be moving if you want to be a stable storm. So it was kind of like, you know, moving up in latitude, and that was kind of the sign that it was going somewhere not good. So yeah, it's gone. But we've seen some other big storms, big storms. None of them have had such titles as Great Dark Spot, though.
Why can't astronomers come up with better names than dark energy, Great Dark Spot, Great Red Spot?
I think you attribute more
Dark
thought
matter.
process to these things. It's like some person at like 4 a.m. is like, dude, there's this great dark spot.
We named our Capitol building the White House and our largest chain of mountains the Rocky Mountains. I don't think we
Right, I'll go with that one. Well, one last time for Dr. Statia.